One way to solve quadratic equations is by factoring. Now we can only do that if the equation is in standard form and it's factorable. But if both of those things are true, then all we have to do is factor the quadratic, use the zero product principle to set each factor equal to 0, and then solve each of the resulting equations. Most of the time we check by simply plugging the numbers in for the variable x and looking to see if we have a true statement. If we do, then that number is a solution to the quadratic equation. And in this case, sure, both of those numbers are solutions. But here's the question. Is there another way to see if we've found the solutions to the equation? I mean, really be able to see with our eyes if we found the solutions. Well, there are a couple of ways, and let's take a look at them. One way we can see the solutions to a quadratic equation is by graphing. Now you might be thinking, what on earth are we graphing? Because we expect to see maybe an x and a y variable in order to graph. Well, what we'll do is replace the 0 in the equation with a y. Now remember that because that's important to understanding how to find the solution to the equation in both the table and the graph. There are lots of ways to graph a parabola, but let's just substitute some values for x, get some values out for y, and graph the points that we get. So when x is negative 4, y is 3. When x is negative 3, y is 0. And when x is 0, y is 3. Now let's graph the points. And sure enough, we've got the shape we expect to see, a parabola, which is the shape we'll find when we graph a quadratic function. But where can we see the solutions to our quadratic equation in the table and the graph? Well, remember what we did to start this off. We substituted a y for the 0. So let's go ahead and substitute back a 0 for the y. And that will give us a clue as to where the solutions to that quadratic equation are in the table. We substituted y for 0 and then 0 for y, meaning that y and 0 are interchangeable. So let's look in the y column of the table and find the 0 values. The corresponding x values are the solutions to the quadratic equation. And there we have it, negative 3 and negative 1. But we've also got a graph, and the solutions to the quadratic equation are in the graph as well. Now remember, we substituted y for 0. In other words, y was equal to 0. And the line y equals 0 is actually on our graph. It's the x-axis. So on that line y equals 0, we have every point that has a y-coordinate of 0. But only 2 of those points are also contained in the parabola. Those 2 points, which are the x-intercepts for the parabola, also represent the solutions to our quadratic equation. So if the x-intercepts are negative 3 and negative 1, then we know that the solutions to the quadratic equation are also negative 3 and negative 1. For another way to see the solutions to the quadratic equation, we're going to look at the world of arithmetic and think about what happens when we multiply numbers together. One way to think of multiplication is with an area model. So if we want to know what 14 times 17 is, we need to find the area of a rectangle that measures 14 units by 17 units. Now, as it looks right now, the area model doesn't really help us a lot in finding the area or the result of the multiplication. But if we think of 14 as 10 plus 4, and we think of 17 as 10 plus 7, we can now think of the dimensions of the rectangle as being 10 plus 4 by 10 plus 7. That allows us to subdivide the rectangle into 4 smaller rectangles, and we can easily find the area of each of those rectangles. So for the first one, 10 times 10 is 100, and then 10 times 4 is 40, and then 7 times 10 is 70, and 7 times 4 is 28. So we have the areas of the individual smaller rectangles. If we add those areas together, we get the area of the large rectangle which is the result of multiplying 14 times 17. Now let's apply that same idea of using an area model to find the result of a multiplication to check our quadratic equation solutions. We factored x squared plus 4x plus 3 into x plus 3 times x plus 1. So if we want to find the area of the rectangle, we can multiply x plus 3 times x plus 1 as the dimensions of the sides of the rectangle. If we find the area of each of the smaller rectangles, x times x is x squared, x times 3 is 3x, 1 times x is x, and 1 times 3 is 3, we have the area of the large rectangle, which we know is supposed to be 0. But with the variable in there, we really don't know what the area is. Or do we? We know that for our solutions, x is either negative 3 or x is negative 1. So we'll take those one at a time. When x is negative 3, x squared is 9. When x is negative 3, 3 times x is negative 9. When x is negative 3, x is negative 3, and then 3 is 3. So if we add those numbers together, we get the total area of the large rectangle, which looks like it's 0, and that's exactly what it was supposed to be. So we've confirmed that negative 3 really is a solution to the quadratic equation by using an area model. Now let's repeat the process with the negative 1, which we believe is the other solution. So let's start with the x squared. When x is negative 1, x squared is positive 1. 3x when x is negative 1 is negative 3. X when x is negative 1 is negative 1. And 3 is 3. So the total of all those numbers is the area of the large rectangle, which is 0. And that's exactly what we needed it to be able to confirm that negative 1 is also a solution to the quadratic equation. So we've used our area model to prove that negative 3 and negative 1 are both solutions to our quadratic equation.